Hi everybody, Mr. Lee here. In this video, we're going to look at kinetic energy, how to do the relationships between variables, and how we can connect work with energy. All right, let's begin. So kinetic energy. Kinetic energy, the word kinetic means motion, zipping around. Now, for kinetic energy, it can apply to anything as big as our sun, and it could apply to something as small as the atoms that make us up, right? But what we're going to focus on is the macro stuff, so the stuff that we can see with our eyes. So that's like, the balls, the cars, the wagons, the boxes, whatever we might come across in our practice problems. And so if it's kinetic energy, and kinetic means motion, kinetic energy is the energy of motion, or the energy of moving objects. All right, simple enough. If it's moving, it has kinetic energy. Okay, so the equation for kinetic energy, and this is something that you should write down. I usually write kinetic energy with KE. Sometimes you just might see it as a capital K. Either way is fine. But kinetic energy is equal to 1/2 times the mass times the velocity squared. All right, so kinetic energy is 1/2 mv squared. And the units for energy, just energy in general, also the units for work is capital J for joules, and it's spelled like Joules, named after a very famous scientist that, did a lot of studies with energy and stuff. Okay, so here we have kinetic energy is equal to 1/2 mv squared. Straight enough, simple, very straightforward. So let's connect this with work. Now, work, we defined it as the force times the displacement. Okay, work is force times displacement, and we gotta think about this. If we are doing work on an object, right? So we are exerting a force on an object so that it has a displacement. Like you are pushing, I don't know, you're pushing a chair or a book around your house, right? You're exerting a force on the object, which is the book, and it has a displacement. So in that case, we know that when the object is moving, it has kinetic energy, because energy, or kinetic energy, is the motion energy, or the energy of moving objects. Okay, so let's think about that. We got to make the connection. If you do work on an object, it can gain kinetic energy. Right? If you do work on an object, it can gain kinetic energy. For example, if you just have an object just sitting there and you do work on it, you exert a force, and it moves across the displacement, it now has kinetic energy because it's moving. And so with that train of thought, we can expand this equation to look like this: 1/2 mv squared. Okay, and so if we were to rewrite this equation, right, like just like a base equation, we can say that work is equal to kinetic energy, like so. Now, I do want to point out that this should actually be the change in kinetic energy. So it's how much the kinetic energy is actually changing. Okay, because if you do work on an object that it's still, the kinetic energy that it gains is from the work itself. Okay, and yeah, so here we have two forms of the equation. They're the same thing, but they work out. All right, now this conceptually ties into something that's bigger, and we will come across this idea again and again. And in fact, one of our topics is called the work energy theorem. But all you need to know until we get to the work energy theorem is that work is related to energy. Okay, work is connected to energy. It's related to energy. It's very important. The two go hand in hand. So now we have to expand our definition of work, because before we saw that work was just force times a displacement, right? If you exert a force on an object and it displaces itself, that's work. But now we have to actually view the scope of all the objects in the universe. If there's a change in energy, if something gets faster, if something gets slower, that means work was being done. You know what? In fact, I'll write that down. If a object gets faster / slower, work was done. Okay, and we know this because kinetic energy is the energy of motion, and work is a change in energy, right? So if work is a change in energy, this time specific kinetic energy, that means work was done. Now, I want to point this out because a lot of the practice problems or the multiple choice problems that you might come across, they'll try to test you on this idea. Okay, and oftentimes if you approach a problem through the scope of energy, it becomes so much easier. All right, awesome. So the last thing I want to focus on is the relationships of variables, and I want to take the time here because we came across an equation where we had the squared variables, but this time we have multiple things that can happen with our equations. So we have kinetic energy is equal to 1/2 mv squared. Yes, I know, I just wrote k, and that's just because I want to get through this. But let's take a look at this idea first called a constant. All right, so a constant is anything, it's usually in a formula, and in that formula is always the same number, okay? Same number. Now here in the kinetic energy formula, this 1/2 is considered to be our constant. The other constants that we came across is capital G, the gravitational constant, and that was, what was it, 6.67 times 10 to the negative 11, I believe? Okay. Another one that we use a lot is the acceleration due to gravity, lowercase g, and that was 9.8, right? So it doesn't matter, for example, if we look at the f of g is m times g, if we looked at that formula, this g, okay, will always be 9.8. Or in our case, we use 10 a lot, right? But this m, this mass, that can change. This force of gravity, that can change. But this g, that will always be a constant. Now, the reason why I want to point out the idea of a constant is because it helps when you know what the constants are, when you're trying to identify the relationships within an equation. So here's my tip. First tip is take out the constant. Okay, so now we have kinetic energy is equal to mass velocity squared, because we're only taking a look at those variables. We don't care about the 1/2. Let's not make things tricky. All right, so I'm going to show you two approaches to identifying the relationships. The first approach is seeing which side of the equation the variables are. So we'll do kinetic energy. So kinetic energy and the relationship between kinetic energy and, let's say, mass. All right, so I'm going to put a line there because I'm going to be listing all the relationships now. All right, so if the variables are on opposite sides of each other, of the equal sign, excuse me, then we know that is directly proportional. Okay, so this kinetic energy variable and this mass variable, they're both in the numerator, they're on opposite sides, therefore they are directly proportional. All right, directly proportional. What that means is if kinetic energy increases, I'll do this in a different color. If kinetic energy increases by a factor, like say by a factor of 5, so if kinetic energy gets multiplied by 5, mass also gets multiplied by a factor of 5. Okay, it's the same. Another one that we can look at is kinetic energy and velocity. Now this is where things get a little bit tricky. So you'll notice that velocity has a squared attached to it, and that is the key. If it has a squared attached to it, so mathematically, like you're squaring that value, then it's simple to identify. It's just a squared relationship. Excuse me, a square, not a squared, because that would be the square root, right? So it's a squared relationship. And what that means is, let's say, so we know that the velocity is squared. So if the velocity increases by a factor of 2, so 2 squared, so velocity is the one that's being squared. So if I increase velocity by a factor of 2, kinetic energy will increase by a factor of 4. Okay, and so that's where the whole squaring comes into place. And with my next method, it'll be a little bit easier to identify that. Right, so, and it's also a one-to-one, or not a one-to-one, a proportional relationship because it's on opposite sides. Okay, so it's a square proportion. All right, next up, I'm going to throw a little curveball there. Look at this. We have velocity squared. So the relationship between kinetic energy and velocity squared. So now we're not looking at the square itself, but we're just looking at velocity. So what I mean by that is technically this can be rewritten as velocity times velocity because anything multiplied by itself is just a square. Okay, so here we have a one-to-one ratio because we're taking a look at this variable v squared as a whole. So in this case, this would be a directly proportional. So it's as if, right, if I were to rewrite this, it's as if instead of saying v squared, I write, I don't know, w, right, because that kind of looks like two v's attached together. Here we have kinetic energy, and here we have whatever this w is, and in this case, remember, w is v squared. It follows the rules between kinetic energy and mass, directly proportional. Kinetic energy and this new variable w, opposite sides, it's just directly proportional. All right, So this here is a stark difference between the two. When you're just taking a look at the variable that is squared, it has a square proportion. If you take a look at the variable and the variable is squared itself, then it's just directly proportional. All right, so get this memorized. This one's an important one. College Board loves these kinds of questions. Okay. All right, next up, we have, if we take a look up here, we have mass. All right, now this is where things get a little bit tricky. I'll draw a line because that's the end of the directly proportional stuff. Let's take a look at mass and velocity squared. Okay, and the reason I want to do this is because I think it's a little bit easier, right? So first check, is it on the same side of the equal sign? No. Okay, so what you can do is I'm going to take this equation up here, I'm going to rewrite it down here, and I suggest that you do the same. So I'm going to move the mass over on the other side, so we get k divided by m is equal to v squared. Now notice, now it's on opposite sides of the equal sign, but mass is in the denominator, but velocity squared, that's in the numerator. So if you have something in the numerator on one side and denominator on the other side, this is what we call a inverse proportion. Okay, meaning that if the value of mass increases, okay, if mass increases, that means the velocity squared decreases. Okay, inverse just means like the opposite. Okay, and also vice versa. So if you have the value of mass decrease, that means velocity squared increases. And mathematically, that does check out. All right, next up, we have mass and velocity. Okay, so if we take a look here, mass and velocity, one is in the denominator and one is in the numerator, but now there's a square that's attached, right? We're not taking a look at the square itself, but knowing in the equation that there is a square. So if it's like this, it's just like what we discussed up here, with a square proportion. So this is a inverse square. Okay, it's a inverse square. Cool. And I think those are all the relationships. Now, that's a lot to memorize, right? But if you're like on the fly, like in the middle of a problem, you need to figure stuff out, here's a strategy that you can use. So just writing out the equation, I like to make it easy on us. Let's make all of these values 1. Right, so we can say that kinetic energy is 1, mass is 1, and velocity is 1. So in this case, we have 1 is equal to 1 times 1 squared. Okay, so if I want to take a look at the relationship between kinetic energy and, let's say, mass, okay, ignore what happens with the other variables, meaning that I don't care about this v squared because we're not taking a look at the relationship between v squared, right? And so here, if, let's say, we make kinetic energy 2, what must mass be so that this equals 2, right? And that's weird for me to say, but yeah, of course, it has to be 2, right? So what this shows us is that if kinetic energy increased by a factor of 2, mass also increased by a factor of 2. And this is a directly proportional relationship. All right. Now, if we take a look at our chart, that fits. It's directly proportional. Okay, it's a 1-to-1. Now let's try the v squared. All right. So if we have k equals mv squared, right? Let's take a look at the relationship between kinetic energy and velocity. So if kinetic energy is, let's say, you know what? Let's do velocity. Let's say velocity is now 2. What will kinetic energy be? All right. So we want to, let's ignore the mass. So we get something like this. If velocity is now 2, okay, so 2 squared is 4. Kinetic energy has to be 4. Now this is not a 1-to-1 ratio, but 2 squared gives us 4, so that gives us our square relationship. Okay, and we can try this with other numbers just to show you that it is not double but squared. Let's say velocity is 3. What would kinetic energy be? K equals v squared, right? So we have 3 squared, which is 9. Okay, so 9 has to be, or k has to be 9. And here, 3 squared gives us 9, and it gives us a square relationship. All right, so that's my strategy for determining relationships. Make everything equal to 1 and take out the one variable that you're not looking at because we're keeping it as a constant, right? And just do the math from there. Change one of the variables, see how the other will change. And from there, that is how you can determine your relationships. All right, so this was Mr. Lee. In this video, we covered kinetic energy, how it relates to work, very important. You know what, so important, I'm gonna highlight this, okay? Because this is what's gonna govern us, our topics in the future, right? Work is related to energy, very important. And we also went over the relationships and how to identify the relationships within equations. I'll see you next time, bye-bye.